Okay, so this ghostly picture is actually that kind of pink and blue is dark matter. Okay, dark matter. And it's mapped kind of like they were talking about. How do we know where dark matter is, right? So we have dark matter and dark energy. The thing they have in common is we just, well, like the video said, I can't really summarize it too much, but they're very elusive. The dark matter, we see its influence of gravity. Dark energy, this is the first time I'd watched that video full through, and I didn't realize that it was like, what did he say, 9 billion years ago, finally, that the dark energy started accelerating our universe. But that's pretty cool. I think we saw kind of this statistic. This is from your textbook with regard to if you were to take the universe and kind of use matter and energy interchangeably, 68% is dark energy, 27% is dark matter, 5% is ordinary stuff, okay? And 0.5% of that ordinary stuff is stars. So you're like, really? So what this does is they talked a lot about, I'll just go ahead and circle this graph right here, okay? What you're looking at, each one of those dots is actually a star in the Milky Way galaxy. And they're saying basically, if you compare it to the middle one is basically the planets orbiting the sun. And one of the things we talked about earlier is that actually Mercury orbits the sun a lot faster than the gas giants. Okay, so you would have thought that when it comes time to look at our galaxy, remember we said what's in the middle of our galaxy, a supermassive black hole, right? I don't know about you, but I think that has a lot of mass. So you would think to see kind of like a similar rotational effect, but we see it flatten out here, okay? And that actually is the effect of dark matter. And not only in our galaxy, but in other galaxies too. Okay, so I think we might have looked at this before, this figure earlier in the class. You might not be able to see it very much, but this disk right here is the disk of a galaxy. There are dots around here that are kind of like maybe ordinary matter that you can see. But can you see kind of the creepy sort of gray stuff? Okay, that's dark matter that basically engulfs most galaxies. And I like what the video said, and your textbook says this too, that dark matter is important in the formation of galaxies. Of course, galaxies are home to stars. So all this is looking at is how can we study, that was the Milky Way galaxy. These are the rotational curves of other galaxies. So each color of a curve is showing you kind of how the stars that are close to the nuclear bulge going outward, how they orbit, and it just kind of is this sort of flat sort of thing. So again, each one of these galaxies has its own little shroud of dark matter around it. Okay. Let's see. All right. So I think the video did a good job of saying how did they map the dark matter in the universe. They actually could do a few things with regard to galaxies, looking at galaxies and seeing that basically they have dark matter kind of around the galaxies. One of the things, I can't remember the name of the galaxy, but remember they said that there was like a cluster of galaxies that they were moving such that too fast that their own matter could not support that movement. Again, they found dark matter kind of strewn throughout the galaxies. This one's kind of, this number 2 is actually kind of pointing to this ghosty thing. Dark matter has an influence on temperature, so we can kind of get a sense for where the dark matter is with regard to temperature. The last one here is gravitational lensing. Both of these actually are gravitational lensing down here. Gravitational lensing, I've heard it is kind of like a dip in the fabric of space and time, and so that light coming in the vicinity of something that is gravitational lensing basically kind of bends around. Here, I don't know if you can kind of see where these arrows are. These arrows are pointing to kind of blue little ghosty things. Those little blue little ghosty things are not the The cool looking orangish kind of things, those are actually, I think I might have looked at it before, galaxy cluster. Those are individual galaxies. The blue thing actually is a galaxy that's farther away, showing up here within this image because of the gravity that's created by that cluster of galaxies. That is so cool. And so, gravitational lensing. All right. So, dark matter, you know, what do you think? Something's got to be going on. So, we see dark matter creating a gravitational influence. Now, we have a couple of options here. Either it really is a gravitational influence, or we don't know much about gravity as we thought we did. And what your author would say, and most people would say, the whole understanding of what gravity does is pretty solid. So dark matter is there. Okay, so what's dark matter made of? And actually, you heard these terms in the video. Okay, I don't know if it was called MACHOs. MACHOs stands for massive, compact, halo. Now the halo part is like the halo of a galaxy objects. Massive, compact halo objects. Well, because a lot of the dark matter we see exists around the halo regions of galaxies. It just doesn't light up. So actually, and this, I know I've seen this on Star Trek. I need to look this up one of these days. Okay, baryonic material, baryonic matter, that's actually just regular matter. So massive MACHOs, massive compact halo objects are just regular matter. Another sort, or what would fall under that category, are brown dwarfs, failed stars, remember? Okay, that would be an example of a MACHO. Okay, it doesn't shine, it's just massive and it's compact. Maybe it's in the halo region. Now, you also heard them talk about WIMPs. The thing about WIMPs is we know that there's not enough normal matter to account for the effect that we see, we call dark matter. So WIMPs actually stands for weakly interactive massive particles. I think that is so cool. Somebody's really thinking here. WIMPs. Okay. So really, probably both MACHOs or ordinary matter and WIMPs are out there, but a lot of WIMPs. Okay. So we saw the guy, he's been doing that for 10 years, still hadn't caught a particle? I don't know, I think I'd about give up. That's worse than the neutrinos, I know. But he's gonna keep trying, okay? That's where like theoretical physicists and observational physicists kind of like, oof. I mean, the theoretical physicist can crunch the numbers, do Einstein's formula, say it's there, blah, blah, blah. But the observational physicist has to go out there and either solidify what the theoretical physicists have already come up with or come up with new information. So, I thought the video did a good job, basically said that dark matter was present at the time that our universe unfolded, and it was like a framework, right? That's actually what you're looking at here. I've heard it called kind of filaments and voids. So the filaments are kind of the stringy regions. This always reminds me of that, you know, that game you get where you have a magnet and there's like a face on a piece of paper and there's filings and you get to kind of make the face. You can make a mustache or eyebrows. Anyway, that's what that reminds me of. So these black dots are actually galaxies that are kind of clustering to regions, to filaments. Over here, let's kind of look for some voids. So there are regions where there are no galaxies, okay? And it's thought that those were void of dark matter. All right, so the last chapter we kind of talked about the Big Bang. Our universe used to be a lot smaller than it is now. This could be like 500 million years after the Big Bang. It's that size, okay? Here it's expanding and cooling, kind of like we talked about in the previous chapter, expanding and cooling. You can kind of see as it cools, we can definitely have galaxies form, but they're kind of forming those filaments and void regions around the dark matter. All right. So 2 more slides, right? Or is this the last slide? Okay, thanks. So there are 4 models, 4 possibilities. And this first possibility, honestly, this kind of, it's called the Big Crunch. Okay, this one right here. Actually, you see the Big Crunch up here? Okay. The several scientists probably talked about, is our universe going to keep expanding? Or is our universe going to expand and then eventually kind of contract and fall back in on itself? For the longest time, they thought it was actually going to stop expanding and can crunch back. Okay, that's what that is. So the way you look at this is this little dot down here. This is the Big Bang. Okay, and then this is present. It says, okay, so it's still expanding. Right. So that actually gives you a certain time since the Big Bang. The second one is called the critical universe. It's critical, yeah. Critical universe. Like this says, the expansion will slow down and eventually stop. Okay. So that's a thought. And it all kind of has to do with, I think the video did a good job. It's a balance between the force of gravity and matter and this dark energy, okay, that they were talking about. The third one looks like this. Okay, where basically the difference here is it's going to continue to expand. Okay, the coasting one would just reach a certain volume and then just go like this. This one just keeps getting bigger and bigger and bigger. Okay, again, it all has to do with, and I'm not emphasizing it much, but if you read about it, it has to do with how much mass and energy was present at the time of the Big Bang. Actually, this fourth one, it's kind of like Goldilocks and the Three Bears. This fourth one actually is kind of fits the bill. I have a picture to kind of show you why they think that this is probably what's happening. The difference here, can you see the cone getting bigger? But the cone is getting bigger faster as it gets up here. So this actually, okay, is one of these. Okay, that's it's getting larger, but its enlargement is accelerating. Okay, so that's actually what we're in here right now. Now with each of them, we get a different initial age of the Big Bang. So here we go. This is the Big Bang here. Okay, it goes back this time. Big Bang here. Okay, in this model, a little bit older, a little bit longer ago, the Big Bang occurred. And in this model, okay, you finally get about what they've been saying, 13.7 or 13.8 billion years ago. Okay, that's when the Big Bang occurred. So you get your oldest possibility here. They actually talked about this experiment in the video. Now each one of these dots here is that supernova, that white dwarf supernova that we said you could use a standard candle. Okay, and it's kind of hard for me to see, but you see the 4 models here. Here's the recollapsing, here's the crunch, here's the critical, here's the coasting, and here's the accelerating. So each one of those dots actually lies on a line most consistent with the what you expect for an accelerating universe. Okay? All right.